Alright, in this video I'm going to go over the US Customary Measurement System. So the US Customary System is similar to the British Imperial System of measurements, but it's not identical because at one point they made a few changes in definitions in the British Empirical System, and they didn't make those in the U.S. Customary System. The United States is the only industrialized nation that still uses that U.S. Customary System, though. So with length, we measure in inches, feet, and miles. So 12 inches make up a foot, 3 feet make up a yard, and 5,280 feet make up a mile. For mass, it's in slug, and I've looked up the history of the slug, but I wasn't able to find much on it. They just indicated that it was a nickname that they had used and then accepted it. So the force is in pounds, time is in seconds, and temperature is in Fahrenheit. All right, so some of those size comparisons, just to kind of visualize, a human hair is 0.004 inches, which is 1/256th of an inch. 2 sheets of paper would be 1/128th of an inch, which is 0.008 inches. And then the diameter of a paper clip would be 1/32nd of an inch, which is 0.031 inches. Oh, and also on these, notice that if I said 1 divided by 256, that is what this would equal. Okay, that's how you get to those decimal points. All right, 1 divided by 32 is 0.031 inches. Okay, whenever you're recording measurements, make sure you always use units. If NASA would have done that with the Mars rover, they would have saved millions of dollars, because all they would have needed to have done was given those units, and the other group would have realized, oh, they're not using the metric system, they're using the US Customary System, and they would have been able to have made those conversions. Those units help a lot, because if I'm grading something and I just see a number, I don't know if you're meaning inches, miles, feet. You might have made an error with rounding at some point, and I wouldn't know because you didn't give me the units. So they're very important. A measurement always includes error. Now, whenever you hear that, that doesn't really make sense, because no, we don't want error. But whenever you make a measurement, or you read whatever device or whatever measuring tool that you're using, you're going to estimate that last part. So say I was using a graduated cylinder, and there's a little bit of space between each of those marks. Well, what happens if it goes right on the mark, or it's just slightly over? We're going to estimate that final number, and that's what they mean by error. There's room for error. Also, like the smoot, they said plus or minus an ear, right? So that's that room for error, or that estimated quantity. And that's why scientists and engineers often use significant digits to indicate the uncertainty of a measurement. Right? It indicates the accuracy and precision of your measurement. All right, so what are those words? Well, precision is repeatability, the degree to which repeated measurements show the same result. And accuracy is the degree of closeness of measurements of a quantity to the actual or accepted value. So with accuracy, someone has went through and they've done an experiment over and over and over, and they continually come up with that same mass, or that same density, and there becomes an accepted or a standard of whatever it is that you're measuring, say a density of lead or something like that. And so whenever you do that same lab, then you should come up with the same thing that they had, or that standard. And that's where their accuracy comes in. Precision is how often do you get that same answer over and over. And the best way that I think that we can explain it is with a target. And this is probably how you're going to see it explained most of the time. But high accuracy is whenever it is hitting the target over and over. And I really wouldn't call this high accuracy, maybe good accuracy, but high accuracy would actually be all of them on that middle part. But we have low precision. Notice that, yes, it's here at the bullseye, but they're sporadically around. Okay. What about this one? We have low accuracy because it's not right there in the target. We have high precision because we keep getting the same value over and over and over. In this case, usually we might see that you calibrated an instrument incorrectly. You need to go back and calibrate it. Maybe there's a certain thing in the procedure that you're doing wrong every single time. It's something that is going wrong and it's occurring every time, and that's why you have a high precision. You're getting that same thing, that same measurement or quantity, but it's not the actual accepted standard, so you know something's going wrong. This is what we're shooting for, high accuracy and high precision. So it's right here on the bullseye, and it's clumped all together. So we have a high precision and a high accuracy. So when we're recording these measurements, right, ideally, again, we're going for both accuracy and precision. Accuracy is dependent on a comparison to a standard, just like we had talked about before, and the precision is dependent on the characteristics and or capabilities of the measuring device and its use. So record only to the precision to which you and your measuring device can measure. So don't ever add extra digits after the decimal. Let me show you why in the next one. I'll explain why you're not going to want to add extras. Okay, so the accepted practice in science is to indicate uncertainty of measurements. All right, because significant digits are digits in a decimal number that carry meaning contributed to uncertainty of the quantity. The digits you record for a measurement are considered significant. Right, include all certain digits in a measurement and one uncertain digit. And just like I talked about the graduated cylinder, if it is, say, if we measure off the graduated cylinder and the increments in between, there's a pretty good amount of space. So if it is 1.7 and I say it's right on there, I'm going to go ahead and add that 0. That extra one uncertain digit. I think it's right on it. Or if it's halfway or just a little over, I might say 1.72. It's a little over it. That last digit is that uncertain one, right? That guess. All right, fractions are numbers in which significant digits are not directly indicated. So significant digits, whenever we look at these, and this is what I was talking about before on don't just add numbers after it, because if your measuring device only goes out to one place after the decimal, you can't assume that there's a higher precision than it is. So example here, 2 grams could be anywhere between 1.5 to 2.4 grams, because 1.5 rounds up to 2 grams, and 2.4 rounds down to 2 grams. So it could really be any of those values in between 1.5 and 2.4. That is a huge difference depending on what you're measuring. Right, so if you use a scale that, I've used one of these before, that goes out 4 places after the decimal. First off, they're about $1,000, and they have a glass box around them. So my fingerprints would even have a mass. So I would have to wear gloves, and I would have to close the box and let it set for a minute, because just breathing on it, the moisture from your breath is also going to have a mass. Right? So you have to close it into a glass box. So 2.000 grams could be anywhere between 1.99995, because that rounds up to 2.0000, however many, to 2.00004 grams, because that would also round. That is not that much of a difference, right, comparatively, right? Because you look at the difference here to here. This one here is a big difference. Well, if I use a scale that only goes out, or it doesn't have any places after the decimal, it's a pretty cheap scale. And there's a big difference in the possibilities that it could be. And that's why significant digits are so important when we're looking at science. And whenever you're recording those measurements, the general rule, a digital instrument you're going to read and record all the numbers, including the zeros, after the decimal point exactly as displayed. That is, like I was talking about, a scale. The decimal scaled instruments record all digits that you can certainly determine for the scale markings and estimate one more digit. That would be like a centimeter ruler going down to millimeters, and then you would have that uncertainty right past millimeter. So maybe it was 2.2 centimeters. Well, I've got the 2.2 for sure because it's got millimeter marks. So I might say 2.20 because I have that extra one that I could go ahead and guess and estimate, or 2.21 if it's just slightly over that mark. Now, fractional scale is a little bit different. With those fractional scales, we really can't record significant figures, and that's why they're really not preferred. All right, but the fractional scaled instrument, I want you to go ahead and record those to the decimal equivalent of 0.00 precision, and that just means 2 places after the decimal. Okay. All right, so typical ruler provides a 12-inch graduated scale in the US Customary units. Each inch is graduated into smaller divisions, typically 1/16 of an increment. All right, so we're going to start with 1, just kind of learn how to read 1. All right, so the division on the US Customary Unit scale are easily identified by different sized markings. The largest marking on the scale identified is the inch. All right, notice that the next mark is just a little bit shorter, and we've halved it. So now we have 2 sections, 1, 2. All right, next we're going to half those. All right, so now we have 1, 2, 3, 4 sections. So this would be 1/4, 2/4, which is a half, and 3/4, which is 3/4, and then 4/4, which is 1 inch. If I was doing this into the decimal, I'd say 1 divided by 4 is 0.25. 2 places after the decimal is how I'm going to record it. Next, we're going to half those. So now we have 1, 2, 3, 4, 5, 6, 7, 8 sections between the 1 inch. And so 1/8, 2/8, which we're going to reduce on down to 1/4, 3/8, 4/8, again a half, 5/8, 6/8, which again 3/4, and 7/8, and then 8/8, which is like an inch. Okay, then we're going to half those. So now we have 16 sections, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you have 16 sections in between here. So this would be 1/16, 2/16, which is an eighth, 3/16, 4/16. Again, you can do the math for these. 5/16, 6/16, 7/16, 8/16, and so on and so on. All right, so that 16/16 would still be 1. Okay, and so that's how you're going to read these rulers. Okay, so let's kind of practice a little bit. So here is on the 1/4 mark. Notice these are the longest, and then the halves are a little bit shorter. The quarters are a little shorter than that. Eighth, a little bit shorter, and then the 16ths are very short. Okay, so this would be a quarter, 1/4. This one, these are all marked into 16ths. If you counted the number of sections, it would be 16. So this would be 15/16. This one here is 1 3/4. The next one is 2 and 1, 2, 3, so 3/8. Okay, 2 and 3/8. And then the last one here is 3 and 1/16. All right, next I want you to play the ruler game. Make sure that you get at least 90 points out of the 100 possible. Take a screenshot and send that in. But the game should help you a lot in understanding how to read that ruler. All right, if you have questions, please ask.